Good morning. This is Ms. Billerbeck, and we are going to talk about the square root function in 10.1. So we have f of x equals the square root of x, and it looks something like this. So we have this point here at 0, 0, this point here at 1, 1, this point here at 4, 2, and then we have this point here at 9, 3. So we can see that if we input a 9 in here, the square root of 9 is 3. Put a 4 in there, the square root of 4 is 2. So we only need the easy points. We don't need all these very difficult points in between. So keep it easy on yourself and go with the easy points for graphing. Well, let's take a look at Desmos and see what the square root function does. All right, so this is our typical square root function here, which is displayed on this graph as well. So we start at 0 and then at 1, 1. That's 1, 1 right there. And then at 4, 2, we see we have another major point right there. Whoops, there we go, right there. And then we would have the same thing at 9 right here. So this would be 9, 3, but it's hiding underneath the picture. All right, so now let's take a look at what these do. So we know this A, what it does on a parabola is it flips it. So I wonder if I make it a negative, what's going to happen? Probably it's going to flip it. So let's take a look. And yes, it sure does flip it. It's just a reflection on around this x-axis, just like the parabola and the absolute value and the line. So it does the same thing for all the graphs. Now we have a little bx here, so let's just ponder what that could mean. So that's just going to make, as it gets bigger, let's see what happens. So it just raises it up. So that means for every value of x, the output is a little bit bigger. But if b is a fraction, let's take a look. So here's the parent graph right here. Now if b is a fraction, it's compressing the graph away from the y-axis as it's a fraction, just like with the parabola, how it is compressed, vertically compressed away from the y-axis. And it ends up getting closer to the x-axis. So, but this one, when we have a b in here, it's called a horizontal stretch because look, it's stretching closer to the horizontal. So when that is inside here and associated right with that x, it's called a horizontal stretch. So as we see, if it's a fraction, it does the opposite and it stretches horizontally as opposed to a vertical compression. You see how that's very opposite? So then if we have a positive value that's above 1, it moves away from the x-axis. So that would become more of a horizontal compression as opposed to a vertical stretch. Okay. So when we associate this value here with the x inside a grouping symbol, it usually is associated with the x-axis. So we refer to it that way. If you just memorize vertical stretch and compression and have that down, the x is the absolute opposite then. Okay. So just so you can memorize it a little bit better. So let's put that back to 1. Okay, now h, what do you think is going to happen here? It's going to do exactly what it did with the absolute value function and the same thing it did with the parabola. So in the vertex form, it's going to move it to the right as we increase it positively. It's going to move it to the left as soon as it becomes negative. Okay, nothing changes with the HK. And the K is self-explanatory. It's just going to raise it up vertically and take it down vertically. All right, so it's just the same old, okay? You keep this format, know this format, know what it does to your graph, you're set. Okay, so let's look at some examples. All right, so it says, let's sketch, state the x-intercepts, or state the intercepts, domain, and range. So this one we see, oh, A is -1. So that's a reflection about the x-axis. Okay, so what we're going to see then is if we have an xy and nothing else has changed, then we see it's just going to look something like that. Okay, so we know that it starts at 0, 0. So we can say the intercept, both intercepts are at 0, 0, the x and the y. Okay, our domain okay, we can write it in inequality format, or we can use the brackets and parentheses. So we know it includes 0 and it goes to infinity. So it's just x is, we probably want to write it x is greater than 0, greater than or equal to 0. If you were using a bracket, you'd have 0, infinity, like that. Okay, so if we had range, well, the range is the y value. So we see 0 is the max, and then it's less than that. It's going to go forever. So it's going to be y is less than or equal to 0. Or if we use a bracket, we have 0 and then negative infinity, like that. Okay. So let's look at this one. So this was the one where we had a fraction in front of x. Now we know if we had something y equals 1/2 or 1/10 x, we looked at it like that, we know that that would just be a vertical compression because it's not in a grouping symbol or anything like that. Okay, so if we look at this being in a grouping symbol, then it tends to be associated with the x. So we would call it, or its reference would be in terms of the x-axis. So the opposite of a vertical compression. So if this is getting compressed, that means it's getting pushed down closer like that. Okay, so that means my x value has to be 10 for it just to reach 1 on the y. Okay, so that's how it gets compressed. All right, so what we have here is a horizontal compression. I'm sorry, a horizontal stretch. It's a vertical compression. So it's stretching toward the x-axis. So, and then let's look at our domain. And the domain is going to be from it's going to be x is greater than or equal to 0. The range is y is greater than or equal to 0. And then our intercepts are at both at 0, 0 is the x and y intercept. So that was easy. Okay, so let's take a look at something that might not be as easy. Well, it could be because we've been talking about this the whole year. Let's see. So how do the following graphs compare to the parent graph f of x equals the square root of x? Well, this one we know it's shifted vertically shifted. That would be even a better way to say it, shifted downward 4. Okay, this one here is horizontally shifted right 10. This one is vertically stretched because the 2 is now outside. So it's vertically stretched by 2 by a factor of 2 and reflected about the x-axis. All right, this one, so the 2 is now inside. So this is a horizontal. Now it would have been a vertical stretch. So what's happening here is this is going way away from the x-axis now. So it would have been a vertical stretch, but now this is inside. So it's a horizontal compression. And by a factor of 2. Okay, so it's moving away from the x-axis, and the x-axis is where the horizontal compression happens. The vertical axis, the y-axis, is the vertical stretch right there. Okay, so depending on what your author and your book are saying, this could be a vertical stretch, but normally when the 2 is in the grouping symbol and associated with the x, it's associated with the x-axis, which would mean that's a compression. All right. So let's take a look at what this might be. So h of x equals the square root of 2x. So we want to find h of 8. So h of 8 is the square root of 2 times 8, which is the square root of 16, which is 4. H of 10 equals square root of 2 times 10, which isn't as easy. So that's the square root of 20. Now that's the square root of 4 times the square root of 5. So h of 10 is then going to be 2 square root 5. Let's look at h of 12 and see if that's any easier. So we have h of 12, and that's going to be square root of 2 times 12 equals square root of 24. Okay, so that's going to be square root of 4 times square root of 6. So that'll be 2 square root 6. Okay, so this one's going to be a little bigger than that one. So then we want to find the average rate of change. Okay, so average rate of change for these two are not going to be so easy unless we actually find the decimal value of those. So let me do that so we can find the average rate of change. Okay, so we have 2 times the square root of 6. So this is the same thing as 4.9. And then we have 2 times the square root of 5. So that is going to be 4.5. So I'm rounding it a bit to make it easier on us. Okay, so now let's find what we're looking for, the average rate of change for this here. So if we look at the average rate of change, it's like slope, but we're going to do h of 10 minus h of 8 over 10 minus 8. So we know h of 10 is 4.5 minus 4 over 2. So that gives us 1.5, which is 1/2, because 4.5 minus 4 is 0.5. So that gives us 1/2 divided by 2. Okay, so when we have a fraction on top divided by a fraction, that's 1/2 divided by 2, which is 1/2 times 1/2 is 1/4. All right, so now let's take a look at this rate of change. So this one we have m equals, and we have h of 12 minus h of 10 over 12 minus 10. So h of 12 is 4.9 minus h of 10 is 4.5 over 2. So that's going to give us 0.4, and then we're dividing it by 2, and that's going to be 0.2, or in fraction form, that's 2/10, which is 1/5. All right, so their average rates of change, this one's 0.25 versus 0.2. So this one's changing a little faster right in here than this one, which is what we would see in. So there's more rate of change happening right in here than there is out here. So that's what we're looking at. The closer we are to our original starting point of the graph, the more there's going to be a higher rate of change. All right, so now let's take a look at this next one. All right, to evaluate the nearest thousands, evaluate each function. So we are just going to do v of 17, which is the square root of 17 over 10. Okay, so that's going to be, that is close to this, the square root, well, it is the square root of 1.7. Okay, so the square root of 1.7, and we want to approximate to the nearest thousand. So that gets us kind of, that's a little tough. So what we could do is say that's kind of, let's just approximate, or actually let's look at what it's between. So 17 is between 16. So the square root of 16 is, we've got the square root of 17 between that and the square root of 25. So it's much closer to the square root of 16 than it is to 25. This is 4, and that is 5. So I would approximate that to be about, I'd approximate that to be about 0.4. Okay, so if we have this, it's about 0.41. So let me check that with the 1.7. It's actually 1 point, this approximates, or actually is 1.304. Okay, so even though we could split that up into square roots and have 4 over the square root of 10. So when we're dividing by the square root of 10, that's between 9 and this one, but it's closer to 9. So what we're looking at is the square root of 10 is closer to 3. And we know that this is about 1.333, 4/3. So we've just approximated both by lowering them down to, so what I did to get this 3 is I said, hey, the square root of 9 is less than the square root of 10 on the bottom. Because let's look at that. Instead of doing the 1.7, sometimes if we know the answer, it's easier to find how we do it. So that's my approach here, because I find these estimates of square roots rather difficult myself. So we're going to do square root of 17 over the square root of 10. Okay, so that's the square root of 1.7, what I had before. So what I'm saying is if we approximate this by dropping it down to the square root of 16 over the square root of 9, we get 4/3. Okay, and that approximates to 1.333, and it keeps going. All right, so let's try this one and approximate it. So we didn't make it to the nearest thousands. I find that a little high of a threshold, but we did get it to the nearest tenth, which is pretty good. So now let's try W17. So we have the square root 17. Oh, you know what? I just found the wrong one. I did the square root here. So we're going to have to swap those. So let me do this one here. So this is the answer for this one. So over 10. All right, so we know that this is approximately 4/10 here. So that's going to be 2/5, which is approximately 0.4. Okay, so let's see what that ends up being. So the square root of 17 divided by, whoops. Okay, divided by 10. So the actual square root of 17 divided by 10 equals 0.4123. So we got it pretty close. We got it to the nearest tenth again by approximating. Now again, this problem is for this. So let me just change this. So, oops, we have the right start to this. Okay, so this is the square root the square root of x like that, and this is the square root here. Okay, so now my questions go with my answers. Isn't that nice? All right, so so there we have it. That's how you would approximate with these square roots. Have a wonderful day. Bye-bye.